Hello, my name is Ken Bradbury. Today I'd like to speak to you about the hydrogeology of Wisconsin. First, let me tell you a little bit about myself. I'm a hydrogeologist and I've worked on groundwater issues in Wisconsin for over 40 years. I recently retired from duty as the Wisconsin State Geologist and Director of the Wisconsin Geological and Natural History Survey, which is part of the Division of Extension at the University of Wisconsin-Madison. I'm excited to give you an overview of the hydrogeology of Wisconsin. Groundwater is probably the most important natural resource we have in our state, and this talk is intended to provide an overview of where it comes from, how it moves, what its quality is, and how we protect it. Thanks for listening.
As an outline of the talk, I will first talk about a little bit about the Wisconsin Geological and Natural History Survey, give a review of Wisconsin geology, talk about Wisconsin's aquifers, groundwater use, groundwater quality, groundwater quantity, and finish with some recent groundwater policy changes. The Wisconsin Geological and Natural History Survey was originally established in 1853 to explore and understand the geology, mineral resources, and water resources of the state. The current organization dates to 1897, and it's now part of the University of Wisconsin-Madison Division of Extension. And you can see here a couple of pictures of a former survey geologist mapping bedrock of the state many years ago. Today, the Wisconsin Geological and Natural History Survey is a vibrant organization that has about 30 staff, and I want to draw your attention to the survey's website here that has a lot of information about Wisconsin's geology and groundwater, and in particular has a great publication library where you can download for free up to 1,000 different maps and publications and reports about geology and groundwater of the state. And again, you can see the website for that. The address for that website right here. This is a talk about groundwater. What is groundwater? Groundwater is water that fills the pores, cracks, fractures, and other voids in geologic materials beneath the Earth's surface, as you can see from this seepage face and along a bedrock outcrop in western Wisconsin. You've probably heard the term water table. The water table is the top of the saturated zone. On the right here we have a cross-sectional diagram of a typical groundwater system. At the surface we have the surface of the ground, and you can see some trees and plants growing there. Then below that we have what's called the soil zone and the unsaturated zone. In this zone, the pores in the rock or soil material may be moist, but they are not full of water. They are unsaturated. At the bottom, in the blue shaded area, this is called the saturated zone, where all the pores, cracks, and openings are filled with water. That's called the saturated zone, and that is groundwater. The top of that zone is a place that we call the water table. The water table is a surface. It's the surface of the saturated zone. Right above the water table, often there's something called the capillary fringe, where water is drawn up into the pores by capillary action. That's only in Wisconsin, usually only a few inches thick, and it's not a real significant thing for us to think about today. Groundwater moves by recharge from precipitation at the land surface downward to recharge the groundwater system and to cross the water table. An aquifer is a geologic formation that stores or can transmit usable quantities of groundwater. This cross-section on the right shows a typical Wisconsin landscape and a number of features about the groundwater system and the hydrologic cycle. It's important for everyone to understand that groundwater and all water originates as precipitation coming from the atmosphere by rain or snow falling on the landscape. Some of that water infiltrates, but the vast majority of it actually runs off and becomes runoff to feed our lakes, rivers, and streams. But some amount of it does infiltrate and becomes groundwater. And you can see as it moves down here under the farm, we see this dotted line which represents the water table or the top of the saturated zone. Below that, we have a couple of different aquifers. We have a shallow aquifer here. We have something called a confining layer or aquitard, and below that, a deeper aquifer. Aquifers, again, are formations that can store or transmit usable quantities of groundwater. A confining layer or aquitard is a unit that allows some water to pass through it, but at a lower velocity. It's a less permeable unit. You can see that groundwater moves from these recharge areas, these upland areas, in groundwater flow paths to discharge into a surface water point like a river or a wetland or a lake. Or if there's a well there, the water can be pulled toward the well and discharged to the well. Some of the water enters that shallow aquifer, and some of the water can move downward to become part of a deeper aquifer if there is one there. Eventually, all that water is going to evaporate or evapotranspire and become part of the atmospheric water cycle, and the system will go around again. Now, where does Wisconsin's groundwater come from? Where is it recharged? Often in my career, I've heard the myth that groundwater comes from Canada. We get a lot of interesting and great things from Canada, but we don't get groundwater from Canada. No groundwater comes from Canada. Moving a little bit south, sometimes we hear that groundwater comes from Lake Superior. That is also a myth. Wisconsin does not get any groundwater from Lake Superior. Perhaps in some wells right near the shore, some water can be pulled back, but groundwater generally is discharging to Lake Superior, not coming from Lake Superior. In fact, most groundwater in Wisconsin comes from relatively nearby, probably in the landscape you can see around you. So in most of Wisconsin, if you go out to the landscape and look to the horizon, groundwater that is under your property or your home has been recharged somewhere within the region you can see from your house. I mentioned aquifers. Wisconsin is a groundwater-rich state and has prolific aquifers. It's plentiful over most of the state. But we also have some interesting and sometimes complex geology here, and so our geology influences groundwater availability and vulnerability. And the takeaway point here is that groundwater conditions vary across the state because of our geology. So let's look at that geology. This is a map of Wisconsin with the various colors showing the different ages or types of bedrock by the different colors. This column on the left is the stratigraphic or time column for Wisconsin geology, with the oldest rocks at the bottom and the youngest rocks at the top, and this extends over almost 4 billion years of time. You'll notice that there are gaps. So Wisconsin's geology does not contain the entire geologic record. Some of those rocks either weren't deposited or were eroded away. So that you can see we have rocks of Precambrian age, which are between 3 billion and 900 million years old, Paleozoic rocks that are between 400 and 500 million years old, and then some younger rocks and Quaternary glacial materials. And those are all indicated by these different colors here. So let's look at a little more detail here. The Precambrian rocks are found in northern Wisconsin in what are called our Precambrian terrain. Again, these rocks are up to a couple of billion years old. They are crystalline rocks that you might see up here like at the dells of the Eau Claire. Our Cambrian rocks are primarily sandstones, and these are the blue-colored rocks that you see in central Wisconsin, and they are exposed at the Wisconsin dells and in other places in southwest Wisconsin. Other limestone, dolomite, and sandstone formations are exposed in southwestern Wisconsin. And if we move over to eastern Wisconsin, we see dolomite of Silurian age. If we look at this cross-section across the state at the bottom of the diagram here, we can see that there's a kind of a dome under Wisconsin called the Wisconsin Dome that's primarily composed of these Precambrian crystalline rocks, and that dome dips out to the east and out to the west, and so our younger rocks, these Paleozoic rocks, are dipping toward Lake Michigan if you're on the east side of the state, or over toward Iowa and Minnesota if you're on the west side of the state. Now let's look again at how these rocks form aquifers. This crystalline aquifer that we see in northern Wisconsin is generally composed of rocks like granite, or rhyolite, or schist. And these rocks are generally non-porous. They don't have a lot of capacity to store water. Well yields can be low. Most water moves through these rocks in fractures or in weathered parts of the formations. If we move to the south, we have a very important aquifer called the Cambrian sandstone that extends through southern and central Wisconsin, and it covers really about 2/3 of the state. This is probably our most important aquifer. It supplies water to many high-capacity and municipal wells throughout southern Wisconsin. And a great place to see this in close-up would be to go to the Wisconsin Dells and go on one of the boat trips, as you can see in the picture there. It's a very beautiful cross-bedded sandstone, very porous, so it contains a lot of groundwater. This rock, these Cambrian rocks, were formed in a marine nearshore beach environment. As you can see here, it's the kind of model that geologists use, and we have different formations going from older to younger: the Mount Simon, the Waniwak, Tunnel City, Jordan sandstones. These are all formed at different times through the Cambrian and Ordovician periods as continental seas came and went and left these sandstones behind in this generally shallow marine environment. And so if we look at these rocks today, you can see why they make such great aquifers. Here's on the left a outcrop over at Rockbridge, Wisconsin, in southwest Wisconsin. You can see how porous it looks, but in close up on the right, you can see these depositional features, these cross beds, and under a microscope, you can see how well sorted this sandstone is, and these grains are rounded and sorted, and they're almost pure quartz. So it's a beautiful aquifer that can contain and transmit a lot of groundwater. Now, if we move up the geologic column a little bit, we get to these Cambrian and Ordovician sandstones that are important shallow aquifers in southwestern Wisconsin. And here you see a large road cut down by toward Mineral Point. And you can see there's a number of different units here. You can see there are seepage coming out along this outcrop because there are minor aquitards in this sequence, and water tends to flow laterally and then out down the slope there. But so it's a more complicated geology in the southwest, and we'll talk more about this in a minute. In the southwest, rivers have cut through the aquifers, and so here's a very old diagram, but still correct, that dates from 1915, and you can see how various river valleys like the Mississippi, the Kickapoo, and Richland Creek, their valleys have cut down through these older Cambrian rocks, so that, for example, the valley of the Kickapoo River is lower than some of these rocks. And here we can have a lot of groundwater discharge into these valleys, which lead us to see springs and even flowing wells, which I'll talk about in a few minutes in these areas. Another view of downcutting in southwest Wisconsin, and the fact that we can have two aquifers here. Here we have an upper aquifer that's composed of the Galena, Decorah, and Platteville and St. Peter formations. We can then have a shale in between called the Glenwood Shale that makes us a minor aquitard, and we can have a lower aquifer composed of these lower sandstones. And so often in this situation you can have, depending on how deep a well is, the water table can be hard to define because water can stand at different depths below the surface depending on how deep the well is drilled. And that can lead to complications and confusion when we understand the hydrogeology of that region. So here we see that shallow wells can draw from the upper aquifer. Here the dashed line means the well is open to that aquifer, and the solid line means it's cased. Here's a deep well that's cased deeply, so it's drawing from only the lower aquifer. So again, Depending on how the well is constructed and how deep it is, you can get water from two different aquifers in parts of Wisconsin. I'm illustrating this in southwestern Wisconsin, but it also occurs in other parts of the state. Moving to the east, we have this fractured Silurian dolomite forming an important aquifer in eastern Wisconsin as it extends from the state line up here toward the tip of Door County. And you can see on the right, here's a picture from an outcrop in Door County showing how these rocks are fractured. They are not very porous on their own, but they have many fractures, and so water can move through those fractures. Here's another example, the escarpment, the Niagara Escarpment at Peninsula State Park. The Niagara Escarpment is a large cliff that goes up along the edge of these Silurian rocks. And if looking in cross-section, we can see why that exists. I mentioned this dome of Precambrian rock that forms central Wisconsin, and that these younger Paleozoic rocks are sort of draped over that dome, and they dip off toward Lake Michigan. And the Niagara Escarpment is actually the erosional edge of these Silurian rocks that forms a cliff here on its western side, and then is shallowly dipping out and disappearing under Lake Michigan. So that would be the Niagara Escarpment in a diagram, and here it is in the real world. By the way, this is the same escarpment that forms Niagara Falls over on the other side of Lake Michigan in Lake Huron. So it's an important feature that wraps around parts of the Great Lakes. Because of the fractures in these rocks, they're very vulnerable to contamination, and you can see this this is a picture of bedrock fractures exposed by alfalfa growing in an agricultural field in Door County. You can see the very regular pattern of fractures, and you can imagine that groundwater can infiltrate rapidly through these fractures. And if these fractures are open enough, you can get water draining really rapidly into the subsurface, as you can see here in a picture from Calumet County. So these rocks can be very vulnerable to contamination, and I'll talk about that more in a few minutes. I like to give people an idea of how deep these aquifers are and the scale of things that we're talking about. And so here in this diagram, we are looking at the Milwaukee skyline from a boat out in Lake Michigan off the port of Milwaukee. And so you can see the buildings in Milwaukee here. And below that, I've shown schematically the hydrostratigraphy, or the different aquifers and aquitars that are present under Milwaukee, and this is all done to scale. So the tallest buildings in Milwaukee are about 600 feet high. And you get an idea then of how thick these different rock units are and how deep wells are. So although there aren't many domestic wells in Milwaukee, if any, most domestic wells across the state range from 100 to maybe 300 feet deep. So they are about half as deep as the tallest buildings in Milwaukee. And they go down to shallow aquifers. Most municipal wells in Wisconsin are between 200 and 800 feet deep. So they are on an order of magnitude as the same depth as the tallest buildings in Milwaukee. But some of the deepest wells in Wisconsin, which are over in Waukesha County, are over 2,000 feet deep, water wells. So they are far deeper than the height of the tallest building in Milwaukee. And I think it's important for people to understand these are major infrastructure developments that people built many years ago for great expense, and that we are pulling water from some very deep places and then pumping it up to the top of the tallest buildings. So groundwater involves a lot of infrastructure and a lot of energy in moving this water around. Now, I've been talking about bedrock aquifers, but remember that there's also shallow sand and gravel aquifers that largely result from glaciation in Wisconsin. Glaciation deposited materials across Wisconsin's landscape between 26,000 and about 10,000 years ago, when the Laurentide ice sheet moved over here. And you can see here that there are a number of lobes of ice that came down and covered parts of Wisconsin, but they did not cover what we now call the driftless area. These deposits left behind sand and gravel and clay Now, clay doesn't make a very good aquifer, but sand and gravel does. And so there are patchy sand and gravel aquifers over much of northern and parts of southern Wisconsin. Sometimes these aquifers are very thin, and sometimes they're not very productive, but sometimes they are. Major aquifers are the central sand plains here, which are a large section of sand and gravel, and then also along some of the major river valleys, like the Wisconsin River here. And so it's important to keep in mind we have this very important shallow sand and gravel aquifer, but it's not continuous. It's in patches across the state. I just mentioned the driftless area. What is the driftless area? The driftless area is the part of Wisconsin that was not covered by glacial materials, which are sometimes called glacial drift, during the last ice age. And this shows up very clearly on our old glacial deposits of Wisconsin map in this area in southwestern Wisconsin that looks different from other parts of the state. On the left here is another similar diagram to one I just showed of where the ice lobes came during the glacial maximum about 18,000 years ago, and that you can see that much of southwestern Wisconsin was not covered by ice. There's been a bit of controversy about exactly what the driftless area encompasses, and the latest word comes from this book by Eric Carson and others from 2019, that it's the part of western and southwestern Wisconsin that was never glaciated and has fluvial incision, meaning it's got a lot of water created deep valleys. And it's really this area surrounded by the yellow line here. The parts of the central sands are not the driftless area, and even parts of Minnesota and Iowa that have sometimes been called driftless are not really the driftless area because there are in fact glacial deposits there. So this is what geologists call the driftless area, is this area right here. Let's turn back to groundwater now and talk about groundwater movement, since we've already reviewed the different aquifers. Groundwater moves from higher to lower hydraulic head. And so in this diagram, the black lines represent what are called water table contours, or also equipotential lines of hydraulic head, meaning they're lines where the water table is at an equal elevation. Groundwater tends to move across those lines from higher to lower elevations, so from the tops of the hills to our streams. But I said it moves in 3 dimensions, and so we also have to think of it moving in a vertical way. So groundwater moves not only laterally, but it can also move downward under the high parts of the water table, and it can move upward toward the low parts of the water table. So it moves in 3 dimensions. And it moves away from these groundwater divides, which are the high points of the water table. Groundwater divides are not fixed in space, but they generally are around the tops of our hills. They can be moved by changes in land use, by pumping, or even changes in climate, but in general they are near the tops of hills, and groundwater moves in opposite directions from these groundwater divides. Where groundwater is moving upward to discharge, we call that a discharge area. And discharge areas are often in places like river valleys. For instance, the Wisconsin River and the Mississippi River and the Great Lakes are important discharge areas. There are also places where artesian wells are likely and springs are likely. I'll talk about those things in a few minutes. Now, what I just showed were some simplified diagrams, but in the real world, groundwater systems are more complicated. So here are some diagrams from our colleagues at the Minnesota Geological Survey, just showing some diagrams that would be similar to southwest Wisconsin, where we have a series of different formations, all having different hydraulic properties, different hydraulic conductivity, for example, and water can move more rapidly from some of these units than others. The water table itself can be very complicated and even move back on itself if we have some aquatards in there. And water can be moving at different directions in different parts of that stratigraphy. And so this is a challenge for hydrogeologists to analyze these flow patterns, but it's important for me to point out that it's not as simple as the diagrams I showed you a moment ago. I showed you that groundwater discharges to surface water, and so it's the groundwater surface water interactions are very important to Wisconsin's hydrogeology. So here you see some people working along the Little Plover River in central Wisconsin. Groundwater provides base flow for Wisconsin's famous trout streams. And on the left here you see a map of Wisconsin's trout streams, and you can see that they are not evenly distributed across the state, but they're clustered in certain places. So each of these little black lines is an official DNR rated trout stream, and you can see there are more of them in western Wisconsin and parts of northern Wisconsin than there are in the east, and that relates to geology. You can also see behind those the colored map, and this is a percentage of total base flow percentage map showing that groundwater base flow, which is the groundwater flow that sustains these streams where it's higher and where it's lower, and the blue places on the map are where the base flow is very high, and that's where you get good trout streams because you have cold, continuous flow of groundwater. Base flow is the groundwater flow that sustains these streams even in times of drought. Even through a hot Wisconsin summer, we have flow in trout streams, and that's because groundwater is discharging to those streams and flowing away. We also have many springs in Wisconsin. On the left is the result of a long time spring survey that was done by the Wisconsin DNR and Conservation Department, and there were over the years over 10,000 mapped springs of all sorts of sizes. On the right are the springs that are larger springs that are over a 0.25 cubic feet per second, which is about 112 gallons per minute. And you can see there are many of those springs as well, although not as many as all of the springs. And you can see where they're clustered. They're clustered, many of them, in southwestern Wisconsin because we have the higher and more rugged topography of the driftless area, and we have all those down-cutting streams through the bedrock. And we also have springs along our major river valleys, along the Mississippi River, and in other places. Springs have been very important in Wisconsin's history. In fact, Waukesha has the nickname Spring City because it was once known as the Saratoga of the Midwest, after Saratoga Springs in New York, which has famous springs. There were very large springs in Waukesha. Spas and bottling plants were constructed there, and people traveled long distances to take in the water and enjoy themselves around the springs of Waukesha, Wisconsin. Unfortunately, due to urbanization, climate change, and groundwater pumping, a lot of those springs, probably the majority of them, are gone now, but it's an interesting part of Wisconsin history. Along with springs, we have something called artesian wells, which are flowing wells that water flows out naturally without a pump. And on the right, you can see a flowing artesian well at the Villa Louis historical mansion over in Prairie du Chien, Wisconsin. Artesian means involving, relating to, or supplied by the upward movement of water under hydrostatic pressure in rocks or unconsolidated material beneath the Earth's surface. And that comes from a French word, artesian, meaning from Artois, a part of northern France where such wells were constructed in the 18th century. How do artesian wells work? And we have a lot of them in Wisconsin. So here you see three different wells in a simple groundwater system. We see the water table right here, and we see a water table well, and then a water table well, the level of water, which is indicated by this blue color fill, stands right at the water table. But in an artesian well, you can see the water in that well stands above the water table. And over here in a flowing artesian well, the water in the well actually flows out at the surface. Why is that happening? It happens here because the top of the well is below this pressure surface of this lower aquifer. And here you can see the water in this artesian well is standing at that pressure surface, but it can't flow out because the top of the well is higher. But here the top of the well is lower and the water can flow out to this pressure surface, which reflects the pressure down here in the lower aquifer. So the water in the well rises to the level of the pressure or head in this lower aquifer. This comes from recharge at higher elevations, as shown on this diagram. So this is maybe we widen our scope a little bit, and over here we have some higher topography. We have recharge from rain and snow that gets into the aquifer up here, and it goes down the aquifer. That pressure is maintained in this aquifer, and as the well is penetrating that aquifer, the water can flow outward here. The time from recharge to discharge can be many years in some cases, so sometimes this flowing water can be very old. Now, Wisconsin has had some very well-known and famous artesian wells. Here's one in De Pere, Wisconsin, over near Green Bay, showing a flowing well in 1890. So here's this looks like one of these Texas oil derricks, but in fact it's a water well, and you can see the water is flowing out up to this level, far above the people standing here. You have people in their raincoats, and it looks like it was a pretty spectacular thing in old De Pere there in 1890. On the left is an old map by Samuel Weedman from 1915 showing the potentiometric or the hydrologic head in the deep sandstone aquifer across the state, and he mapped with these blue dots the artesian wells that they knew of at the time. So there were wells in eastern Wisconsin, artesian wells also in other places like western Wisconsin. And so Weedman and Schultz, his colleague, put together a book in 1915 about underground and surface water supplies of Wisconsin. And they said that flowing wells are common along valley bottoms of the Mississippi and the Wisconsin and up many of the side valleys leading to these main streams, and that these wells get their supply from the upper Cambrian sandstones. And they pointed out a lot of wells along the Mississippi River, and one of the most interesting one was a well at the city park, now the library in Prairie du Chien, Wisconsin, where you can see this well flowing up to 60 feet above the surface. And I love this old artistic rendition of this well in the park at Prairie du Chien as a centerpiece of the city park, flowing quite a bit above the ground in this fountain, and people enjoying the well. And it's quite interesting that Prairie du Chien was one of the first cities in Wisconsin to have a municipal water system because of this flowing well. Unfortunately, this well has now been abandoned, and the flow decreased quite a bit over the years, so it doesn't exist anymore. But it's a really interesting snapshot of Wisconsin history. Now I'd like to move to groundwater quality concerns. Certainly in this talk I don't have time to go into much detail about all these things, but things that people are concerned about in drinking and groundwater. And let me just list them. The number one thing I think should be pathogens, things that make you sick. These would be bacteria, viruses, protozoa, which are often related to human or livestock fecal waste. They've been detected in many private wells and also in some deeply confined aquifer wells. Next, we think about nitrate. It's probably Wisconsin's most widespread groundwater contaminant, mostly related to agricultural practices, but also to waste disposal. And then we think about arsenic and other naturally occurring elements that can be mobilized through well construction. Arsenic is a naturally occurring element or parts of minerals that exists in some of our bedrock aquifers in Wisconsin, and has been a problem in recent years. We have pesticides, atrazine and other agricultural products that are put on the ground by humans for good purposes, but can get into our groundwater and cause problems for people. Radionuclides, which are naturally occurring elements in Wisconsin. They can occur at low levels, but they can be carcinogenic if in too high a level, and can be problems in some of our wells. PFAS and PFOS, which are relatively new contaminants that result from manufacture of things like fire retardants and waterproofing materials that are now being found at a number of sites around Wisconsin. And the health effects of these are not completely clear. Right now, the state is just now developing standards and policy for these PFAS and related chemicals. And then we have many other emerging contaminants, things like pharmaceuticals, PCPs, or personal care products. And these are things that are used in the home all the time and that we throw down the drain. They generally come from wastewater or solid waste sources. And there are other contaminants too, but I've listed the things that most often I've gotten questions about in my career. On the right, you can see a map of the state by county showing the estimated percentage of wells over the nitrate standard. The darker colored counties are higher, more wells over the nitrate standard. And so you can see that some of the counties have 15 to 20% of the wells exceeding the nitrate standard, which is not a good thing. To learn more about contaminant hydrogeology in Wisconsin and what the state's doing, a great reference is the annual report to the legislature that's put together by the Wisconsin's Groundwater Coordinating Council and is available for free from the DNR website at the web address shown on this slide. This is a map of the relative susceptibility to groundwater contamination from near-surface sources. This map was put together by the state survey, the DNR, and the U.S. Geological Survey almost 40 years ago now. And it's an educational map that shows you the basic controls on groundwater contamination, which include depth to bedrock, type of superficial materials, type of bedrock, soil characteristics, and depth to the water table. And in general, to look at the map, the redder parts of the map are most susceptible, and the green are less susceptible. Now, this doesn't tell you whether groundwater is going to be contaminated or not, but it does show you the relative risk from place to place. And I think a takeaway is that much of the groundwater in Wisconsin is quite susceptible to contamination, so we need to be vigilant about that. In particular, areas where we have karst and shallow fractured rock are vulnerable. So karst is a landscape created when water dissolves rocks such as dolomite or limestone, which are soluble carbonate rocks, and create holes, passageways, or caves that water can move through rapidly. And fractured rock is also very vulnerable to contamination because fractures don't have much capacity to cleanse or filter contaminants. So on the left here you see a typical karst landscape where you have things like sinkholes, caves, large fractures, sinking streams, and so forth. And this would be the kind of landscape we see in parts of eastern Wisconsin and parts of southwestern Wisconsin. On the right is a map of places where shallow carbonate rocks occur. So carbonate rocks would be rocks like limestone or dolomite, and where they're between 0 and 50 and greater than 50 feet from the surface. And so as a hydrogeologist, I would say that this rocks in these areas are really quite vulnerable to contamination because they can contain these fractures and solution cavities. Here are some pictures of karst features in the driftless area where we have sinkholes, conduits, and caves, and weathered carbonates that produce a red clay called terra rossa. So here's a sinkhole near Blue Mounds, Wisconsin. Here's what we call a conduit in a road cut. Here's more conduits or weathered places in dolomite. And here's part of a cave in southwestern Wisconsin. So these are places where groundwater could move very rapidly with little attenuation of contaminants. I want to spend a couple of minutes talking about a recent study that I worked on along with others called the Southwest Wisconsin Geology and Groundwater Study, also known as the SWIG study, which we conducted from 2018 to 2022. This study examined groundwater quality in Grant, Iowa, and Lafayette counties. And during that study, we sampled 840 private wells for bacteria, nitrates, and in some cases for some other pathogens. And the full report of this study is available at the website shown on the slide here. And the idea was to try to understand what the water quality, the drinking water quality was in these 3 counties in southwest Wisconsin. One of the interesting things that I've concluded from this is that water quality there were problems with water quality, and those problems were very generally distributed. And so here you see a map of with a lot of spots on it, and the red spots are wells that were positive for total coliform bacteria or high nitrate, and the clear spots were places where they were not found. And you can see that there were many wells where we did have positive results and many wells where we did not. But what you don't see is a cluster here. In other words, there's not one single contaminant source that's causing this. These are distributed over almost equally over the 3 counties, suggesting that this is more of a land use and a large scale problem rather than can be pointed to some kind of bad operation at one spot. So what our key findings from this week's study were that between 42 and 27% of the wells sampled either had high coliform bacteria or high nitrate, which would make them really unsuitable or problematic for drinking water. It was discovered that human wastewater and livestock manure contribute to private well contamination, although human wastewater was the more common of the two. Pathogenic genes, in other words, genes that can make you sick, were detected in 66 of 138 wells that were sampled for those things. These included both human, animal, and non-specific sources of these pathogenic materials. And contamination was related to well construction and land use factors. And again, I refer you to the report, which is extensive for an understanding of these findings. Now, one of the things that we did want to point out, though, is that the potential for cross-contamination through cross-connecting wells. I've showed this diagram earlier where you have the upper aquifer, this Glenwood Shale, and this lower aquifer, and you can have shallow or deep wells. Now, in this case, I've shown this deep well has an open casing, meaning it's open to the shallow aquifer and the deep aquifer. The shallow well next to it is only open to the shallow aquifer. And we have 2 different water levels. Here's a water table in the shallow aquifer. Here's a water table in the deep aquifer. Now, if contamination is present, having that open well means that the contaminants, even if it's only present in the upper aquifer, can move down this open hole and get into the deep aquifer. So the well itself becomes a contamination source. And for that reason, we recommend that wells be cased, if they're going to go into the deep aquifer, be cased through this upper aquifer and only open to the deep aquifer. That's an easy way to help protect the deep aquifer from contamination. To learn more about water quality, there's a wonderful resource for you all called the Water Well Quality Viewer, which is available from the University of Wisconsin Stevens Point at this address on the slide here. It's an interactive mapping application that lets you look at different parts of the state and different counties for a number of different constituents in groundwater. For example, here's nitrate concentrations by county. Here's bacteria by section for a part of a county. And here's a list of all the different common constituents that you can look at with that application. So it's a very, very useful tool. Now let's turn to groundwater use. In Wisconsin, we use about 207 billion gallons of water per year, according to the DNR, which is a lot of water. And this map shows generally where it's used. This is a map of high capacity wells that are permitted by the DNR, and the color of the dot represents the type of well it is. And you can see that, for instance, what jumps out at me is in central Wisconsin we have a lot of green dots. These are irrigation wells, agricultural irrigation wells. So you can see they're clustered around our agricultural regions. They're clustered along the Wisconsin River. Here's more over in northwest Wisconsin by Eau Claire and over toward the Twin Cities, some in southeastern Wisconsin as well. But not so many in northern Wisconsin where we don't have as much irrigated agriculture at all. We also have a lot of municipal water systems, which are the blue dots, which, as you would expect, are clustered in our population centers, like near Waukesha here, near Madison, down toward the border here, along the coast, around Green Bay. Again, fewer of these in northern Wisconsin, where we have smaller populations and smaller cities. Although we do have individual wells for cities, but sometimes a village in northern Wisconsin would only have 1 or 2 wells, where a city like Madison might have 20, 25 municipal wells. And then there are other wells, industrial wells, aquaculture wells, and so forth. What are some of our water quantity concerns? Well, when we put these high capacity wells in, this pumping can cause 2 things: drawdown or lowering of groundwater levels near the well, and reduction of groundwater flow to a nearby surface water features. In other words, a reduction of groundwater discharge. And what we see here is that when a well is put in and pumped, you get something called a cone of depression, where right around the well, the water table is lowered in a shape of a cone. And so here are 2 wells. If they don't pump at the same time, each well would have its own cone of depression. But if both wells are pumped at the same time, those cones of depression merge, or wells interfere with each other, and so the cone of depression becomes broader and a little bit deeper. And in fact, the wells are influencing each other, and this is what we call cumulative impact. The cumulative impact of adding the impact of these wells together. And that is an important concept, which we can see illustrated quite well here right in Dane County. So this is a map of Dane County. Madison is right in the middle of this map, and here are the Yahara lakes, Lake Mendota, Lake Monona, and so forth. And each brown spot is a high-capacity municipal well. And as you might imagine, most of them are clustered right around Madison. We have 2 aquifers, essentially in Madison, a shallow water table aquifer and a deep sandstone aquifer. And while each well has its own individual cone of depression, this map shows you how those cones merge to make larger cones of depression that are somewhat deeper. And the shallow cone of depression looks a little bit odd here because it's limited by discharge from the Madison lakes. The deep cone of depression is not controlled by the lakes, and so it looks a little more realistic. And it's up to 90 or 100 feet under parts of Madison in the deep aquifer. So this is the cumulative impact of all the pumping wells around Madison. So cumulative impacts are important to understand. Another place where we've really seen cumulative impacts is in the central Wisconsin sand plain, where we have thousands of irrigation wells. So this is a map of parts of central Wisconsin. This inset is a map of the Little Plover River watershed that I'll talk about in a minute. And each little dot here is a high-capacity well used for irrigation of crops like potatoes and corn. And there are many of these wells have gone in, really increased since 1960 to present day and onward. Again, thousands of these wells now. And understanding how these wells interact has been a very important thing. So a few years ago, we looked at this along the Little Plover River, which is just southeast of Stevens Point, and to see how these high-capacity wells were affecting the river itself, and did some computer modeling that's written up in a bulletin from the WGNHS, Bulletin 111 from 2017. And we found an interesting graphic here. I'll show you. Is that on the left here is a map, and this blue area is the capture zone or the contributing area where groundwater was flowing into the Little Plover River prior to any irrigation wells, high capacity wells being installed. And we do this through computer simulation. The Little Plover River itself is this little blue line right here, and you can see that this was a fairly broad area. Now, after the wells were installed, we have this area on the right, which looks a lot different. It's kind of jaggedy because these individual wells are diverting some of the water that would have eventually gone to the river, and the entire cone or the entire capture area is smaller so that there's less water to flow in the river now, and that is why the flows in the river have decreased over the years. And we were able to show this pretty well through computer modeling. Other computer modeling that's done recently was the Central Sands Lake study that was done by the Wisconsin DNR and others back in 2021. They were looking at the impact of these high capacity wells on levels of lakes in Wisconsin, which was a difficult problem because there are a lot of things that can impact lakes, such as climate change and just annual changes in rainfall. But they concluded that for example, Plainfield Lake here, with current irrigation agriculture, the level in the lake is down a bit from what it would have been with no irrigated agriculture, and that has impacts for many things like fishing in the lake, the recreational opportunities, the aquatic life in the lake, and so forth. And this is a very good report that was been written up by the DNR and is available from the DNR website now if you want to read about it. Now, just to finish up, I want to talk a little bit about the water quantity laws in Wisconsin. I've been mentioning high-capacity wells. And what is a high-capacity well? A high-capacity well is any well that can produce over 70 gallons per minute. That's 100,000 gallons per day or more. And under recent law, it's a high-capacity property is if the number of small wells on a single property adds to 70 gallons per minute or 100,000 gallons per day, then the property becomes a high-capacity property. So this was to prevent people who want to maybe look for a loophole in the law to get around it by putting in a few small wells that would add up. So that whole property is now considered high-capacity property. And a high-capacity well requires a permit from the DNR. And the DNR has to review these permits, and so they are thinking about things like the drawdown from the well and impacts on surface water features. So things that they look at are, is it in a groundwater protection area? That is an area where we're looking at to protect trout streams or springs. Is there over 95% water loss, meaning is that water being taken for, I see, a bottling plant and shipped out of the watershed? Does it impair a public water supply? Does it degrade the groundwater resource? Does it cause significant adverse environmental impact? And does it have cumulative impacts on other wells? So those are all things that the DNR considers when they're reviewing a high cap application these days. But those things have changed over recent years, and those changes began back in 2011 with something called the Lake Beulah decision, which was an important legal case that came to the Wisconsin Supreme Court. And in a nutshell, what happened is that the village of East Troy, which is over in southeast Wisconsin, wanted a new water supply well. And they were adjacent to this lake called Lake Beulah. And the owners, the property owners around Lake Beulah, were concerned that this new well for the village would harm their lake. And at the time, it was argued that the DNR did not have the authority to worry about did not need to, or even have the authority to worry about what might happen to the lake. All they needed to worry about was whether this well was going to be adequate. And that of course, was an argument, and it went to the Wisconsin State Supreme Court. And the Supreme Court found that the DNR did, in fact, have the authority and also the duty to consider whether the proposed high-capacity well could harm waters of the state. And that was an important legal precedent that led to the Wisconsin DNR doing a lot more study of high-capacity wells in their permitting. And so in 2011, the DNR began to consider the impacts on surface water and looking at cumulative impacts of wells during their approval process. But this became controversial, and in 2016, our Attorney General issued an opinion that the DNR did not have the authority to do this. And so the DNR in 2016 had to stop evaluating these cumulative impacts. But as you might imagine, there were many lawsuits over this. The permits were granted by the DNR. A judge threw out the permits. The DNR countersued for reinstatement of the permits, and there was a lot of confusion in 2020 when a new Attorney General opinion reversed the previous opinion, and the DNR must now consider cumulative impacts. And since 2021, the DNR has been evaluating the cumulative impacts of high-capacity wells. And so this is just some headlines from 2020 showing that this was a pretty big deal, that the DNR was going to consider high-capacity impacts on bodies of water, and it represented a different political change, which could change back depending on politics, frankly. So let me summarize what I've just talked about today. Wisconsin has a complex and rich geology that governs its groundwater resources. Both our bedrock and our unconsolidated sand and gravel aquifers provide water for wells. Groundwater is plentiful over much of the state, but there are local areas of scarcity. Pumping and drawdown have impacted surface water in some areas. Overall, groundwater quality is very good, but there are a number of threats and local issues. I will stop there and thank you. For more information, I would recommend looking at the Wisconsin Geological and Natural History Survey website and also the Wisconsin DNR's website, and the addresses are given here. Thank you for your attention.